There are many things in the world that seem illogical. There, when you actually look closer, are logical explanations to many of them. For example, psychology has been trying to do this for a very long time, trying to draw logical patterns and conclusions out of the chaotic mess that we sometimes are. People have always fascinated me for this reason. However, most psychological explanations don't quench the thirst of those drawn to mathematics and physics. But these fields seem to be counter to the world of emotion and behavior. Let's just take this as a challenge. Now, I know that most of you are familiar with the concept of physics. You know, the laws that work to explain, define, and predict the movement of mass and energy throughout the universe. And psychology, which is basically the study of how and why we behave, think, and feel. There is no unified theory of psychology. Rather, over the years, many psychologists have put forth different explanations as to why we are the way we are. In recent years, the study of neuroscience has taken a front seat in the world of psychology. The key difference from early schools is that neuroscience aims to explain psychology through science, such as by using chemistry and biology, i.e. certain chemicals acting on specific structures of the brain create thoughts and emotions. So what does any of this have to do with physics? Through the research I provide here, my aim is to show the base evidence and correlations needed to support a hypothesis that the laws of physics are applicable in the study of psychology by looking closely at Newton's laws, the theory of relativity, and electro and linear dynamics. I will demonstrate how these ideas can be applied to Freud's theories on suppression and repression, Skinner's definitions of behavioralism, and the mechanics of neuroscience. A good starting place is to look at macro applications of physics and psychology. I spoke to Professor of Physics Randy Tagg and asked him what his opinion on this was. He related the human psyche to turbulence. This is what he had to say.
Another sort of non-living complex system that we've studied, that I've done research on, is turbulence. And turbulence is inherently very unpredictable and complex, and yet it arises out of fundamental equations of motion that we understand. So we learned that there are some ways that we can begin to get a handle on turbulence in terms of some broad-scale descriptions of how a system will evolve to a particular state, which we would say it sort of settles into what we call an attractor. And so, I'm interested in knowing the extent to which this concept of an attractor would be applicable to brain states. Does cognition represent some kind of the formation of an attractor that we associate with some concept?
Basically, Randy is saying that if you look at small pieces of even a seemingly random system, they still obey certain patterns and laws that we know. Also, that there is this idea of an attractor, which is a perpetuator of a state of being, and that has relation to how we form thoughts. So basically, the perpetuator of a state of being like something that would make you happy, something that would make you mad. Sir Isaac Newton was one of the founding fathers of what we know as physics. And even though many of his ideas have been expanded on or corrected, he has left us with 4 very important laws regarding motion. For our purposes, we will be dealing with only his first and third laws. Newton's first law states that every object will remain at rest, or in uniform motion, in a straight line, unless compelled to change its state by the action of an external force. This law has correlations to Skinner's definitions on behavioralism and conditioning. Namely, that the entire concept of conditioning is based upon the fact that there is a certain action or inaction that is to be changed. And to change this, the controller, teacher, or nature, by the use of some stimuli, administer a new force to counter the action or inaction presented. This is how we learn. For example, in the case of the Skinner box, an animal is placed in, and the goal is to teach it to flip a lever so that it can release itself. When first placed in the box, the animal remains at rest. It has been given no incentive force. The third law states that for every action, or force in nature, there is an equal and opposite reaction. Now say we look at emotion as a force. It is generated deep inside the brain and is directed outward, resulting in a physical response. If we use this definition and look at suppression and repression, we then observe an explanation for Freud's findings. If emotion is a force that is being generated in the system, but not permitted to leave, eventually the pressure in the system will become too great and it will rupture. Perhaps some of you are still skeptical. After all, what does emotion have anything to do with force? How does it have physical properties? So, As unromantic as it may be, emotion, or at least the physical production of emotion, is only a certain pattern of electrical and chemical stimuli. So why does any of that matter? Because this was proved by a series of differential equations derived from data produced by electrical spikes, or in other words, physics. I'll let Randy explain the experiment.
One of the most beautiful models connecting physics to neurology is something called the Hodgkins-Huxley model. It was absolutely beautiful, brilliant piece of work that was done in the 1950s, where they came up with a quantitative description about how electric potentials could exist and then be generated as potential spikes, called action potentials. And so they came up with a system of differential equations that described the time dependence of the voltage across the membrane in terms of these constituents, and came up with this enormously rich insight into how the process works. And what I like about that in particular is that it was really a nice illustration of the application not just of physics, but of my subfield of physics, which is nonlinear dynamics, a combination of physics and mathematics, to the operation of neurons.
So pretty much anything moving and anything electrical can be explained and predicted through electro and nonlinear dynamics. There are so many other areas of physics that can be related to psychology, but that must be saved for some other time. So, can the nature of human emotion and perception, as illogical as some claim it, be described through a world of strict physics? The answer isn't so simple. There are so many experiments that have already been done using physics to help solve problems of a psychological nature. It is almost a given that our psychology, on a macro level, must also be determined by the laws of physics. The most important thing is that we accept physics not as a separate science, but as a tool of logic that can be powerfully used like biology and chemistry to further our ongoing endeavor to explain our psychology and quench the logical and mathematical thirst.